Good morning. Happy Monday. Today we'll be talking about, the point of today is to show you in reasonably well rendered pictures what I tried to draw poorly on the board before. And this topic is what the electrical engineers would call microfabrication, but because we're really in the nano regime now, we're going to go ahead and call it what it is. So why do we care about nanoscale structures? And some of you a couple of years ago may have seen me talk at the orientation event, or perhaps the nano engineering recruiting event. You might have seen this slide before, but I love this slide because it shows all of the, in sort of striking detail, all of the materials and phenomena that occur on the scale of 1 to 100 nanometers. And this is the size confinement effect in semiconductor quantum dots. So we talked about how as you shrink the dimensions of a quantum dot, you increase the band gap. These are all fluorescent. They're all excited at the same maybe UV frequency, and then they emit at increasingly low energy frequencies. Then we have the strength and exceptional charge transport properties of carbon nanotubes. This is a gecko foot, which of course adheres by capillary forces to surfaces. No, it's primarily due to van der Waals forces, and while there is a dependence on relative humidity, it's principally because you change the mechanical properties of the keratin of which the gecko foot setae and spatulae are actually made. This is the Lycurgus cup, which is made during Roman times, and it's red not due to any dye molecules, but actually to gold nanoparticles. So people 2,000, well, however many thousand years ago, are actually practicing nanotechnology. And in fact, red stained glass is often made using gold nanoparticles, and they scatter and resonate at visible frequencies, and that's why you have this red color. And interestingly, I put this structure here, which is a microchip, as an example that is a little bit unlike these examples. The effects of size confinement in microprocessing are regarded as something to be suppressed as opposed to be something to be exploited. So you really don't want leaky capacitors and leaky gate dielectrics in your transistors, which are sort of the effects of quantum confinement. So this is really a classical type of device, but it's made using really sophisticated techniques of nanofabrication. But in any case, nanotechnology, this is why you're all here, is in some sense regarded as the future of medicine, catalysis, separation, sensing, information technology, and also energy from both the standpoint of conversion, as in solar cells and triboelectric charging, piezoelectric charging devices, and also storage. So storage meaning batteries and so on. Okay, so nanofabrication can be conveniently separated into two regimes, the mastering regime and the replication regime. So nanofabrication as a whole includes both the generation and arrangement of structures, usually in the lateral dimension of 1 to 100 nanometers. So mastering is the creation of new nanoscale information in a form from which it can be replicated. So typically in the semiconductor industry, this takes the form of electron beam lithography, or scanning beam lithography as a whole, where it could be a focused ion beam or an electron beam. An electron beam is generated from a very hot tungsten filament, and then it's focused and moved around using electromagnetic fields into very small areas. And because the electron beam has a very has a mass because it's not a massless particle like a photon, it actually diffracts much less than a photon, so you can confine these electron beams to very narrow line widths. So you can actually make lines in polymer electron beam resists like a photoresist, but it responds to electron beams instead of, or in addition to photons, to make structures that are 5 to 10 nanometers even in lateral dimensions. So this is an electron beam writer. You'll notice it looks a little bit like a scanning electron microscope. So if you've used one, or if you haven't used one yet, you definitely will as a nano engineer. Use an SEM. And what you'll find in general is that when you make a new technique of nanofabrication, you're usually exploiting some characteristic of some characterization technique, because characterization techniques tend to be developed first, like microscopes. You use the optics that you learned by making the microscopes to make a photolithographic stepper. Similarly, you use the scanning electron microscope, which makes which detects the scattering of electrons off a sample and reconstructs a three-dimensional or two-dimensional image. And you can also use the electron beam to write patterns. So instead of looking at objects, you're using it to actually create objects. So here's sort of a cartoon of how it works. The electron beam comes in and it makes this pattern soluble where it impinges on this E-beam resist film. Then you wash away where it says pattern, and then maybe you etch the master. Say this is a chromium film on a quartz substrate. This could be used as the photomask in photolithography. So don't worry about what is actually happening in the chemistry in terms of the mechanism. I just want to show you that we do know what's going on the molecular scale. This is polymethyl methacrylate, or polymixed martial arts, PMMA. And what you do is you take this this polymer and you irradiate it either with light or, in this case, with an electron beam, and it undergoes some bond scission here. Don't worry about the details, and you break this polymer apart in a form that is now soluble. So that's the important aspect. This is a positive resist chemistry, which means that as you shine light or electron beams, you render the pieces of the regions of the film that are exposed to be soluble. On the right-hand side, and thanks to the Chemical and Bioengineering Department at Georgia Tech for providing these images. If you use an epoxide-based resin, you actually can create covalent bonds using a photoacid generator. Don't worry about that for our purposes, but the point is, when you irradiate it with electrons, an electron beam, or with light, you tend to cross-link the film, so you make it hard and insoluble. So here you make it soluble, here you make it insoluble, where you impinge where the beam impinges on the film. So therefore you get a negative resist pattern. The pattern you get in the resist film is the opposite of what you have in the mask. The next step after mastering is the replication step. So E-beam lithography, while it's sort of the no-compromise way to generate very small patterns, it's very slow. So it takes many hours or a day to make a copy of some pattern. So what you want to be able to do is you want to be able to take the mask that you made by E-beam lithography and make many replications. So for example, photolithography, which is the principal way which replication is done, can take a 300 millimeter wafer and process it per minute. This is an exposure tool. So basically, you take the mask that you made by E-beam lithography, and this is a simplified drawing. Usually, you're going to be reducing this image down using optics onto a photoresist film, and then you just crank them through one after the other to make this pattern smaller on a silicon wafer. This is a 193 nanometer exposure tool, like the one that you might find at Intel or Samsung or AMD, and these are really expensive. perhaps on the order of $50 million. And the reason that they're so expensive is because in order to produce this pattern and to get it down to a size that's equivalent to like 100 atoms across or 50 atoms across, which is what today's technology requires, you have to make these optical elements with nanometer precision, right? You have to arrange them in space, and they have to be ground to a radius of curvature with that is not very tolerant of faults. So this instrument is typically in a fabrication manufacturing facility that contains many such instruments, and the fab itself is typically designed originally to make one kind of one type of chip, and the factory into which this goes is built for that chip, and it costs maybe $3 billion to build just that factory. So you better not have very many errors. Okay, here's another image that explains the difference between positive and negative photoresist chemistry. So you take the substrate and the resist film. The resist film is maybe 10s to 100 nanometers thick. Could be thicker than that if you're talking about making, say, microfluidic chips, and you need to master a microfluidic chip against a hard master, and you might want this to be tens of microns. But in the semiconductor industry, it's going to be in the tens of nanometers thick. So you take this mask that's say the quartz isn't shown here, but the transparent regions generally, or the transparent regions are. So the light goes through and you expose these regions, and then the negative pattern, they harden, and you can do whatever you want to the substrate. And in the positive configuration, these parts become soluble, and then you can do whatever you want to the underlying substrate. So see, here and here you have the opposite patterns. This is another type of photoresist chemistry, and they work by different mechanisms. Don't worry about the chemistry at all. I just want to show you that there are molecular details here if you're interested in it. So you have this Novolac resin, which is really an old type of polymer that if you had like a Fisher-Price record player or something from like 1960 or 1970, God knows why you would have that, but it was made of this stuff called bakelite. And it was very brittle and whatever, but it's used in photoresist chemistry quite often. This isn't the state-of-the-art photoresist that's used in today's chips, but it was used for quite a long time. What it has is a dissolution inhibitor. The dissolution inhibitor is called diazonaptoquinone, or DNQ. So these are called DNQ Novolac style photoresists. And when you irradiate this nitrogen group here really wants to leave. It really wants to become free and be nitrogen and increase its entropy. So what you do is you irradiate it, and the nitrogen swims off, and then this part here collapses into this carboxylic acid, and it goes from being something that's hydrophobic to something that's hydrophilic, because this group is very polar and it can ionize. So then as a result, if you wash aqueous base over this film, you etch out the regions that have been exposed by the light. This is a plot showing Moore's law. So in your first homework in week 1, I asked you to sketch out a few plots, a few points on this plot. So Moore's law says, there are a number of different formulations of Moore's law. It says that, for example, the number of transistors on a microprocessor doubles approximately every 18 months or so. And you can make similar arguments for the density of devices in a charge couple device or a memory chip, the capacity of a memory chip. But this shows it really strikingly. I could show you where all the computers I had growing up here are. So we had an 8086 processor. Of course, this was before I was born, but it was given to our family by a family friend, and we used that for a while. Then we got, on October 10th, 1993, we got our 486 computer, and I remember the date because I used to mess around with my computer a lot, and it would tell you when the operating system was first activated. That happened to be Windows 3.1 back then, which had just come out. And the other reason I know is because my sisters really wanted to use the computer that evening, and then they were showing Star Trek reruns that night, and I had never really watched like the original Star Trek, but I got hooked, and that date, October 10th, 1993, just became drilled into my memory forever. Okay, and because you really care about this, the Pentium 3 was our family's next computer. We got that in 1998. Yeah, it's about right. And then, I don't know, all the grad school and work computers are somewhere over here. What are the limits to photolithography? So we can't, light diffracts, right? That's the first thing we learn about the quantum mechanical character of light, is that you shine it through a pinhole or two pinholes and it diffracts. So sometimes it's a particle, sometimes light is a wave. The wave-like aspect of light is particularly problematic in imaging technology. So resolution is limited by diffraction. So R equals K lambda over NA. NA is the numerical aperture. Lambda is the wavelength, K is a system-dependent constant, and R is the resolution. The resolution is typically expressed as the minimum feature size that is possible, so the half pitch. The pitch in a processor, if you approximate a memory device as a bunch of word lines and a bunch of bit lines, the pitch is the distance, the center-to-center distance between features on a chip. The half pitch, therefore, is roughly the size of the feature itself. And these are, believe it or not, kind of loose definitions, but it's in general the size that it's reasonable to reach. Anyone know what the half pitch has reached in 2017? If you bought a state-of-the-art microprocessor in 2016, you know what the half pitch was? 14 nanometers. The 11 nanometer node was revised down, which is surprising because it reflects that we're actually better than we thought we were going to be at beating the diffraction limit. The 2017 node is actually the 10 nanometer node, and the production facilities are now cranking those devices out. I think Samsung is the first company to have a commercial 10 nanometer device. K is the proportionality constant, which is a system-dependent parameter that reflects the sensitivity to fluctuations in exposure intensity and temperature, so real experimental aspects. So if you have these lenses that are arranged with say tens of nanometer precision, single nanometer precision in some cases, and the temperature increases, the temperature fluctuates around some equilibrium value. Like, you better hope that and these lens materials have thermal expansion coefficients that are significant in some cases. You better hope that your thermostat is accurate on the wall, right, in your production facility. Otherwise, the entire batch is going to be ruined. So the K proportionality constant, we can get this down by making the materials really tolerant, and our environment in which we manufacture these things really tolerant. About 0.3, and it's believed to be impossible to get this below 0.25. Lambda is the wavelength that's currently 193 nanometer excimer laser. And 193 nanometer lasers, there's a company that was based out of, that was actually a PhD thesis at UCSD called, that became the Cymer Corporation, which is what is named the lecture halls in the SME building, which endowed the lecture halls in the SME building, and it was recently purchased by ASML, which is a Dutch semiconductor manufacturer. So anyway, UCSD has a big role in the development of photolithography. 193 nanometer light has been used for a long time, like 10 years, but we're making 10 nanometer features now. So we're doing a lot of cheats, right? Because how can you take something that's 20 times the light that's 20 times the resolution that you need? How do you get that to work, right? So that's what we're going to talk about in the next few minutes. 157 nanometer light was abandoned largely because It might still pop up eventually, but it's not really being used now because the lenses and the immersion fluids and the actual stepper machine itself has components that absorb 157 nanometer light. So obviously that's no good. Numerical aperture is n sine theta, which is the acceptance cone of an optical system, and it's proportional to the refractive index of the medium. That's all I know. Okay, how do we beat the diffraction limit? How do we take 193 nanometer light and get it down to producing features with line widths and spacings that are on the order of 10 nanometers? So current processors, like the Intel Core M is probably a better one now. How do you make that with 193 nanometer light? Well, one way is to use immersion optics. So remember that the numerical aperture, which appears in the bottom of our resolution equation, can be increased by increasing the refractive index of the medium. So what you're doing is you're essentially you're effectively reducing the wavelength of the light if you have a high index medium. In general, we use water, so that gets you a good factor here, 1.33 instead of air. But your processes have to now be compatible with water because now there's water between your lens and the chip that you're making. Phase shifting masks. There are a couple different kinds of phase shifting masks which produce optical interference at phase shifted features, and they enhance the contrast or even produce new features, and we'll see how that works in a moment, or right here. So here's the non-phase shifted light that comes through, where we have light that has troughs and crests, and then we take a phase shifted region, and what happens at the border lines between the shifts in phase, and how do we produce something that has a shift in phase. So here's a normal transparency mask. This is one that we've made by e-beam lithography. This is quartz, and you have these opaque, say they're chromium pieces. Then what you do is you take a region in here and you etch a little bit out of it so that the light coming through here is now of a different phase than the light coming through here. Another way to do it is to have a partially transmissive opaque feature that actually does allow some light through. That's a way to change the phase of the light between here and the adjacent region. So how it works is this. If you have a conventional mask and you have two apertures that are small compared to the wavelength of light that you're using, what's going to happen is when you shine the light through these two apertures, the light will constructively interfere because you have this light beam and this light beam, and when you add them together, the superposition looks like this, and the intensity, which is the square of the superposition, looks like this, and you have one feature. So you wanted two features, but now you have one feature. In contrast, if you have a phase-shifted region, which could be made using one of these methods, you now have a field amplitude that looks like this. This is now out of phase with this one. A superposition looks like this one, it looks like this, and the intensity now is two features. So you've now doubled the amount of resolution that you have simply by having adjacent regions with opposite phases. Another trick is to use multiple exposure patterning. And these techniques are used ubiquitously in photolithography, and they work in general by this method. It's pretty intuitive. So just starting at the bottom, suppose you wanted to make a structure that looked like this. Don't worry about what a hard mask and the device layer is. Just say this is all silicon. If you wanted to make features like this that were 50 nanometers apart and you're using 193 nanometer light, could you have one mask that just had holes in it like this? No, you'd get no resolution at all. You just have one, you just expose all the photoresist at once because there would be constructive interference everywhere. So instead, what is done is using basically two coatings of photoresist. You take the first photoresist layer, you pattern it at at double the pitch that you want. So half the resolution, double the pitch. Then you get rid of this photoresist layer, you spin coat and expose another photoresist layer, and then you pattern it in the in-between regions. Now, why didn't, and then you can etch through and you can make this. So it took 2 masks and 2 photoresist layers, but we got the structure that we wanted. Now, why couldn't we just take the same photoresist film and then switch out the mask or move the mask over by a few nanometers to make the other pattern? Why couldn't we do that? Same photoresist film. Here we had to coat a brand new photoresist film. Why couldn't we use the same one and just do the exposure twice? Yep.
Because it was already exposed.
Yeah, so it was already exposed in the edge regions. Like where we wanted the exposure, that's fine, but where it diffracts, that's bad, right? Because those are sub-threshold exposures, which are actually producing some of the chemical reactions that cause the film to become soluble later. So what that's called is a sub-threshold exposure, and what we're asking the film to do is forget the sub-threshold exposure, which it can't do. There are, however, chemical engineers and polymer engineers that are working on photoresist films that can actually forget sub-threshold exposures. So you do some heat treatment or something, and the photoresist film can actually forget that it's been exposed in the areas around the exposed region. So in this case, you only need 1 photoresist film and you get the pattern that you want, but you need 2 masks still. Another technique uses the fact that the sidewalls of the polymers, the sidewalls of the photoresist features themselves actually contain information. So you can grow films on sidewalls that become sort of like a secondary resist. In this case, you have your photoresist film and it's patterned, but what you can do is you can make a spacer. So you grow some kind of spacer layer by chemical vapor deposition or by atomic layer deposition or some kind of process that uses the fact that you could grow stuff on the sidewalls. Okay, so you've grown stuff on the sidewalls of these features that you made. Then you can take these negative areas and you can deposit what you want in there. So now you had something that had a very low resolution, and now you have all these little features in here that you can do whatever you want with just by using the sidewalls as actually containing information. Now, if you use the right kind of etch chemistry, you can get something with a much greater resolution than the mask you originally started out with. So all of these techniques combined with immersion optics and phase shifting masks are the techniques that you use to cheat the system. They're the techniques that you use to get high resolution features from very long wavelength light. Yeah.
Why can't we just use like 2 sources of light that will constructively interfere with
Yeah, the question is how come we can't use 2 sources of light that constructively interfere? And the answer is in some circumstances you can. But it's more used in the research lab than in manufacturing. But I'll show you in a few slides how you can do that. Good question. Okay, so multiple exposure is very expensive because it more than doubles the number of steps, and double exposure is promising. And actually, this I think made it out of the research lab relatively recently. So this is one of the tools now that if it's not being used yet by semiconductor manufacturing, it will be soon. Okay, this is a fun slide. When I was in grad school, a paper came out in 2008 by C. Grant Wilson, who's a professor at UT Austin, who along with Jean Frichet, who's now at Berkeley, when the two of them were at IBM, their research teams developed what's called chemically amplified photoresist, which became the basis for high-resolution photolithographic patterning. And what Wilson did is wrote this article in ACS NANO 9 years ago now, but it's interesting because they went to the CIMATEC conference, which is the semiconductor industry trade group, and they had all the world's top experts in the room, and they did a survey, and they said, okay, comparing 193 nanometer dry single exposure, so none of the tricks we were talking about, This is where semiconductor manufacturing was at the time. Then immersion single exposure. So we get the refractive index benefit, but then 193 nanometer dry plus 193 nanometer immersion double patterning lithography. So combining all the double patterning techniques. Then high index lithography, which is if you have a higher index material other than water, can you, like oil or some kind of special high index oil, can you actually get even smaller features? Extreme UV, which is the 157 nanometer, which actually they thought by 2016, which obviously just ended, was going to be the winner, right? They thought this was going to be the winner. Nano imprint, which is where you make, instead of a mask using e-beam lithography, you make a quartz stamp and you press the stamp into the photoresist film, and that's how you do the patterning. And then ML2 is maskless lithography, which is why it's called ML2, is using e-beam lithography to do all your replication, where you have multiple electron beams doing all of the fabrication at the same time. So they thought this was going to increase a lot, and then it was going to increase, and ultimately the trend was going to be that maskless lithography somewhere out in 2025 or so was going to be hugely important, and extreme UV might by then have died off. But what actually happened is that instead of this 193 nanometer dry, 193 nanometer immersion curve, which was supposed to be basically down to nothing by 2017, is now up here. So we have continued, not we, but the people that do this professionally have continued to push the envelope using the techniques that I've described, and these really high-end sort of approaches haven't really taken off yet. I am not one of those professors that will tell you that Wikipedia is crap and that you should never trust what you read on it. Some of the articles, many of them are actually quite good. The one on next generation lithography is very good. So this goes through all of the different techniques that I've been describing, the resolution and the issues and the throughput and the tolerable defect sizes. So I encourage you, if you're interested, to look more into this, and you can start here. All right, now in a research lab and in patterning biomolecules or patterning structures for energy conversion, we often don't need $3 billion fabs and $50 million steppers in order to make our structures. So this has actually spawned quite a large area of research in nanoengineering that we would call unconventional nanofabrication. So the tools of standard photolithography are very expensive. They tend to be not very accessible because to get into a clean room, you need to pay for a clean room, and they cost a lot of money for a university to maintain. In fact, I wrote this book chapter a few years ago on the energy use in a clean room, where this was actually the clean room use at Harvard in 2007. So the data are old, but the trends are the same. This used 27 million kilowatt hours per year, which was 2% of the energy budget of the entire university campus. This was a 10,000 square foot clean room, still is, and has quite sophisticated stuff in it, and so 2% of the energy budget, hugely expensive. So the tools use a lot of electricity, and then HVAC systems and lighting and air polishing and all the stuff that you don't need in a classroom that you do need in a clean room. I should say that in a fab, so in an industrial fab, this slice of pie is actually about half, and the HVAC systems actually need a lot more energy than the tools do. So compatibility, often organic species and biologics are incompatible with the tools that you use in clean rooms, and they're not allowed in the clean rooms. Often we're interested in non-planar, mechanically compliant, and very small and disposable form factors, so flexible hybrid electronics, not necessarily rigid semiconductor wafers. And the techniques invented for semiconductor manufacturing are considered, are really quite overkill. So we talked about the error rate that's allowable in semiconductor manufacturing at being about 1 part in 10 to the 18 error rate. So that's the acceptable rate of error. What if we don't need that rate? What if 99% is fine? We don't need 1 part in 10 to the 18, which might be okay for chemistry, biological applications, sensing, medicine, optics, materials for energy, tend to be more tolerant of defects than microprocessors. Also, philosophically, there's this idea that nanofabrication has to be something that's difficult. It requires wearing a bunny suit and a face mask and a clean room, when in fact there's nanoscale information all around us. We just have to use the right tools to find it. So we can find nanoscale information in cracks, shadows, and edges between structures, sidewalls, defects, lattice steps, and other discontinuities. So even you take the cross section of your glasses and the Scotchgard coating is nanoscale. And it also allows us to repurpose analytical tools. So this is a typical thing in nanofabrication, is that we take like a microscope and we repurpose it. So instead of examining the nanoscale world, we're using it to create, we're co-opting the technology to create the nanoscale world. Okay, one technique that is involved with a lot of, that is sort of the basis of many other techniques of unconventional nanofabrication is soft lithography. And what soft lithography requires is that the key feature of soft lithography is that the pattern transfer step involves a soft or polymeric stamp. So typically what's done is E-beam or photolithography on a silicon wafer, and maybe these are photoresist features, or maybe it's actually etched silicon, and this is just monolithic. This is a monolithic thing. Then what you do is you pour in an elastomeric prepolymer. Now almost always this is polydimethyl siloxane, which is just normal silicone rubber, and then you cure it so it's a cross-linkable silicone rubber, and then you peel it out, and you can do a number of things with it. So these features, while I've drawn them here macroscopically, they could be as small as 10 nanometers. So you can ink the stamp using a nanoparticle ink or conductive polymer ink, or maybe even decals like metallic films. You can take them to a substrate and just do simple printing. You can do molding and embossing using, say, a thermally or UV curable prepolymer. You can do phase shifting edge lithography, which is taking these, so this mask is transparent because it's silicone rubber, and you can shine light through it, and actually at the edges of these features you get either constructive or destructive interference that can either cure, in the case of constructive interference, on a negative resist, or not cure. I'm distracted by the number of people on their phones right now. Okay, so and you can create images where the sidewalls were, right? So you take something with, say, a micron feature here, and you can get down to like 50 nanometers using these constructive interference patterns. And this is actually using the technique of phase shifting lithography that's used in the semiconductor manufacturing industry. This area here is what I actually did my PhD thesis on, which is using mechanical sectioning to generate copies of structures. So you take the stamp, you make an epoxy replica of the stamp, then you metallize the thin film, then you take a cutting tool and you get like 100 copies out of this by cutting into the plane of the board, and then you get these slices that have features that are where the lateral features was determined by the thickness of what you deposited on the sidewalls. And the reason that this is potentially a useful tool is that making structures thin in the vertical dimension is easy, but making structures that are thin in the lateral dimension is hard. So what this does is it converts something that's thin in the vertical dimension to something that's thin in the lateral dimension. Yep.
How are we cutting something that small?
So this is done using and this is still just in the research lab, but this is done using a tool called a microtome, which makes structures for transmission electron microscopy. So you put the structure in, and the key thing that it has is a single crystal diamond blade that's polished to a 2 nanometer radius of curvature. So it creates a crack tip, and which travels up the workpiece, and then a section slides off. It's almost like a nanomechanical deli slicer.
Really sharp knife.
Really sharp knife. You can also, and this is actually important in many of you will use microtoming not for fabrication, but rather for TEM sample preparation, which is what the technique was designed for. There are also oscillating blades, which have maybe a 400 nanometer amplitude, but vibrate at say a kilohertz or something. And as you move the blade back and forth, it's a little bit like sawing bread with a knife. And what this does is it prevents the slabs that come off from being compressed, and like a piece of bread. So say you have a knife, very sharp knife, and a loaf of like French bread, and you just press straight down on it. What's going to happen? The bread's going to squish, and the pieces of bread that come off are going to be squished. But if you saw, even if it's not a serrated knife, and you saw it, the slice that comes off is not compressed, right? How does that work? It's actually a very interesting geometric argument. You actually increase the effective sharpness of the knife, because as you move a knife with respect to the workpiece, and you draw the path of travel from one end of the knife to the other as you move it, and you project that angle down, you actually have a sharper edge, a sharper effective edge, because of the relative motion than you do of the knife itself. So next time you're cutting bread, be aware of this argument. You're actually making it sharper by oscillating the knife back and forth. Not literally, but the perspective of the bread, the knife is sharper. It has something to do with relativity and Einstein. Okay, so here's a really simplistic drawing of the molding process, and basically this is pretty simple. You have the photoresist, you make the PDMS stamp, and then you replicate the structure that's in the PDMS stamp in a piece of hardened epoxy. You can do this on curved surfaces by using a high modulus polymer here, but it's thin, so it's flexible. Anything that's thin is flexible. But you have a rigid, and you have an elastomeric, a softer elastomeric backing, and maybe something that's rigid just so that you can manipulate it. And then you can bend this thing around curved surfaces. So this is how you might pattern a curved surface, which you could never do in a photolithographic stepper. You can make structures from air bubbles, for example. So you can mold stuff so this is a block copolymer film. This is polystyrene, and then poly mixed martial arts. And what you do is you expose this to UV, and we know that PMMA behaves as a photoresist or electron beam resist. So you can get holes in this pattern, which look kind of like this. And then you can coat PDMS over them, and maybe they'll form air bubbles, and you can actually get the impression of the nanoscopic air bubbles in the PDMS, which can serve as the basis for further replication. Yeah.
How did it happen? Because did they expose or how like just?
You might get that by increasing the temperature and just having the pressure bulge out a little bit. So how low can you? That's a good question. The question was, how do you make the shape concave? So what are the limits to molding with polymer films or with prepolymers? It turns out that you can mold things with atomic scale precision, and this discovery was you take a silicon wafer that's a single crystal you made by sawing the big ingot of stuff. Then you glue it to a hard backing, and you create a crack And then before the crack ends, so if you have something that's cracked but not completely cracked, what it tells you is that at the very end of the crack, you have two sides of something that's separated by one atom, right? Because the next angstrom in, it's not cracked anymore. So logic says that there's a 1 angstrom or 2 angstrom or whatever atom you're using or step edge. And indeed, this is what happens. If you take the pre-polymer, you can actually measure this by atomic force microscopy to be a step edge of 0.4 nanometers, which is about the van der Waals diameter of a silicon atom, approximately. This is some unintentional artwork created by me in the lab like 10 years ago, but it's really cool, so I'll show it. These are very high aspect ratio pillars that are coated with metal. They're 200 nanometers at the top, 500 nanometers at the bottom, and they're 8 microns tall, and the pitch here is 2 microns. And you can actuate these things by shining electron beams at them, and they'll bend like octopus tentacles. When you do physical vapor deposition, sometimes you get these unwanted nodules of metal that are ejected all at once. So instead of getting atoms ejected, you get big blobs. And this blob looks like the moon was caught by 2 of the pillars. And I took a picture of it because it's really quite a striking image. So photolithography is very good at making things with straight sidewalls and things. Yeah, there's a question in the back.
Some of the slides before. So after you shine the electrons on them and they bend it, if you stop shining the electrons, do they return their films?
In this case, yes, but they don't have to. If there was some chemical change, then they wouldn't. Yeah, so the question was, if you remove the electron beam from this from this image, and actually the electron beam is just that I was focusing here and then zoomed out before they had a chance to recover. They will eventually recover, unless say this is an E-beam resist and you're actually doing chemistry and hardening it even further, then in principle it would stay like that. Yep.
What's the origin of the color differences? We notice they're kind of like whiter on the ones that are bent backwards. So
yeah, so the origin of the color difference here is because these were evaporated with gold from an angle like this. So these pillars are actually biased to bend in only one way because they're coated with metal on one side and not the other side. And you can actually see the shadows here. These are not shadows from the sun. They're shadows from a beam of gold atoms. Okay, so we can also make interlocking structures and structures with open, with closed loops by taking a master membrane or master that has a membrane. So the master structure could be photoresist that we make using 2-photon lithography. And this gets back to your question. How do we use constructive interference from 2 light sources to make a 3-dimensional structure, which you can do here. So if you cross streams, which in Ghostbusters terminology is a very bad thing to do, but don't cross the streams. But if you cross the streams in photolithography, you actually get constructive interference at the intersection of the 2, in this case, lasers. And what you can do is carve out 3-dimensional patterns. And if your master structure has a very thin membrane in it, then when you pour PDMS silicone rubber over it, you have the PDMS, and you take the PDMS replica off. The PDMS will actually seal to itself because this membrane is not thin enough to keep them apart. So when you take the replica, you peel it off, seal them together, then you inject another kind of prepolymer into the channels created, then they can't get into the region that was originally defined by the membrane. So this is a way to make complex structures before and after removing the membrane, and this is like a nanoscale solenoid, for example, microscale. You can use, this is so exciting. What if we finish up a little bit on, you know what? I'll just finish up now so we can do a new topic. Okay, this is how you make shape selective nanoparticles using a very low low surface energy polymer. So this is the last example that I'll show. You know how when you buy rubber galoshes, the last time you bought rubber galoshes, and around the seam there's this seam that looks like it was made from two separate halves of a mold, and you press it together. That's called the flash layer or the scum layer. It tells you how they feel about it, right? And someone goes through with some scissors or a razor or something and they cut that off. And that's anytime you have a molded plastic piece, you always have this seam. You always have this flash or scum layer. The same thing happens with replica molding on the nanoscale, that the pre-polymer film, when you mold a film, has this layer that connects the particles. In order to get rid of that layer that connects the particles, you can use a very low surface energy mold like polyperfluoroether, and this work is done by Joseph D. Simone's group at NC State, and you press it into this pre-polymer, then you lift it off, and you get these separated particles that are not separated by a scum layer. It's more like an ice cube tray. Put the ice cube tray down, the ice cubes you smack it, and the ice cubes are all separated. And you can make ice cubes that have different shapes. I have ones at home that have Darth Vader's head on them, but you can make whatever ones that you want. So, and what's interesting about this is if you make these particles using drug molecules, you can actually study shape-selective endocytosis. So how does a cell pick up or not pick up a drug delivery microparticle or nanoparticle because of its shape? And that's where I will end today. Thank you very much for your attention.